Welcome back, ladies and gentlemen. In this video we're looking at the idea of conservation of energy and a few related, associated ideas. And we'll also check out a couple examples of how this idea works, how it comes into play. First, let's look at some different types of energy. There are many different forms of energy, and some of these terms that I know you've heard before. There's kinetic energy. There is something called potential energy. You might think of that as the potential to do something. There are two common kinds of potential energy, though, and we're going to deal with one of them here. One is gravitational. And another common kind is spring energy, an energy in a spring. Well, we're not going to get into the spring energy right now, but we will definitely be using gravitational potential energy along with kinetic energy. But there's other kinds also. There's thermal energy. You want to think about heat, thermal energy, right? There is chemical energy. How do you get energy? Chemical energy. How do you get energy from the food that you eat to do the things you do? To contract your muscles, pump your blood, think the thoughts. Well, there's energy stored in the chemical bonds of the food. You digest it, and your body has these wonderful processes that take place inside of cells to convert the chemical energy into other forms and make it useful. There's also this weird thing, and we're not going to get into this. It's called rest energy. And this is something that Einstein started trying to figure out, and there were some other people also. Kind of an idea that is now roughly 100 years old, maybe a little more. But if you think about Einstein's famous equation, E equals mc squared, that's sort of what rest energy is talking about. There's an energy associated with stuff. Even if the stuff isn't moving or doing anything or is not located anywhere special. So, however, though, we are going to focus on just a couple of these different types of energy. Right there. We're looking at kinetic energy and gravitational potential energy. Kinetic energy is the energy of something that is moving, motion. And so if it's moving faster, it has more kinetic energy. Potential energy, gravitational potential energy, is the energy of an object's position. So an object on a low shelf has a small amount of potential energy. An object on a high shelf has more gravitational potential energy. Now, all forms of energy can be measured. How do we look at these things? All kinds can be measured in units of joules. Joules. We'll abbreviate with a capital J. And, well, what is a joule? 1 joule is equivalent to 1 Newton meter. And a Newton is force, a meter is distance, so you have force times distance. This is just like work. But we saw earlier in a previous video, work is for the most part, equivalent to energy. And they actually do use the same units. But a Newton can further be broken down, if you were interested in doing so, into a kilogram meter per second squared. And when you multiply a Newton here times another meter, the meters get squared there. So this is how the units break down, how they're related. Okay, now there are some simple equations. Let's look at that real quick here. Simple equations for kinetic energy. We usually abbreviate KE, and we have 1/2 mass times velocity squared. So if something is going faster, it will have a larger kinetic energy. There's also a pretty simple equation for potential energy, and I usually just say potential energy, even though what I'm talking about is gravitational potential energy. So we need to know the mass. We will multiply by acceleration due to gravity, and we need to know some height. Okay, so the height is a measurement of vertical distance above some reference line. And you'll see how this works when we look at an actual example. But height is just, it's how high it is above something. Okay, now the thing about these two forms of energy, when you combine kinetic energy and potential energy, you get what's called mechanical energy. And we just use a capital E for that. So this guy is called mechanical energy. That's an A, mechanical energy. Okay, that's this guy. And it's simply the combination of an object's kinetic energy plus that same object's potential energy, right? It's a lot like keeping your money in two separate bank accounts. Okay, we could let's kick this up a notch and say you've got $1 million, right? So we're going to use an analogy. We're going to use money for this analogy. You've got $1 million. You're going to put it into two accounts. You could have account A and you could have account B. And we're not really too concerned with why you have these two accounts, but you're going to see that this analogy will help you understand total mechanical energy along with kinetic and potential energies. So what are you going to do? Where are you going to put the money? You can keep the money in account A, B, or split it between the difference, split it between those two accounts. Let's say you put all $1 million, wouldn't that be nice, into that account. Then how much must go into account B? Nothing. Let's say you kind of split it even. You got 500,000 here, and that means you have 500,000 to put in account B. And you can do something a little silly, like you can say, I'm going to put $1 there. Well, that leaves you with $999,999 for the other account. But regardless of how much you put in each account, the total, you got to recognize, is going to be the same. You have an amount that you're adding together there, you have an amount that you're adding together there, or an amount that you're adding together there, and they are all the same value. Your total wealth is the same no matter where you put the money, in account A or account B, or split it any way you want. Your total wealth is the same. In other words, it is conserved. That's what we say. Well, it's conserved. You don't gain or lose any money simply by putting some of it into a different account. I've got money there and money there, so I've got more money. No, if only that's how it worked, right? So in fact, you know what the total is. The total is your $1 million. And so however much you have in account A plus however much you have in account B must equal $1 million. And it doesn't matter how much you have in each account. Not necessarily, right? Now, what this means is, in terms of, there's our money analogy. In terms of energy, energy is also conserved. Energy works just like that. As long as no work is done, then the total energy remains the same. And that means energy is conserved. So there are two accounts where energy can exist, and the two accounts are the kinetic account, so to speak, and the potential account. And the sum must equal, well, this thing called total mechanical energy. And you can move you can move energy from one account to another. You can transform energy from kinetic to potential or potential to kinetic, but the total must still be the same. All right, That's what we mean when we say energy is conserved. This guy is unchanged. Conserved, that's an S. Right? That's what we say. All right, so now at this time we need to look at an example, and I think this will make some sense here. So, let's look at example number 1. We're just going to drop a ball from a height of 2 meters and see what happens. Okay, so we've got this ball, we're going to drop it a distance of 2 meters. And so there's our 2 meters. Right here, there is an amount of mechanical energy that the ball has initially. And down here, just before it hits, there is an amount of mechanical energy the ball has just before it hits. So there's an initial mechanical energy and a final mechanical energy. In each one of these, you ought to be able to put this together for yourself. Each one of those mechanical energies is made up of kinetic plus potential. So this guy is made up of a kinetic energy plus a potential energy. But those are initial values of each one. This guy is made up of a kinetic energy and a potential energy, and those are final values of each one. So here's the kicker. When we say that energy is conserved, what we're saying is that the total is unchanged. So from initial to final, there is no difference. Those are the same. So I can say that they are equal. That and that are equal. And that's how we start off working this out. I'm ultimately going to say that I'm looking for how fast it's going here right before it hits the floor. So here's how I start this. Just like that. And then each one of these expands. I'm gonna write this part and this part, and we'll see some cool stuff happen. Okay. So we have to realize this is really, we're applying conservation of energy. As soon as you see just even that, you want to recognize conservation of energy is what you're using. It's the physical idea or the physical law that you're applying here. Okay, so I'm going to expand each of these bits because from those simple equations, I know that kinetic energy is 1/2 mv squared. But I need to be using the initial velocity. Potential energy is mgh, and I need to use the initial height. So expand these also. mv squared, this is final velocity, that's final, so final. And mgh, and final, it all matches up. Okay, so I'm just gonna plug some numbers in and see what I end up getting, right? Kind of wall this off so I don't get myself a little confused. I have 1/2, and the mass. I need a mass. The mass. Let's make the mass 1.5 kilograms. Okay, mass of the ball 1.5 kilograms. 1.5. Forgive me for leaving the units out, but I'm going to try to conserve some space. And I'm conserving so that I can make it all fit here. A velocity. Well, my initial velocity, if this thing is dropped, the initial velocity is 0. 0. So my mass again is 1.5. G is always going to be 9.8 here at Earth's surface. H, my initial height. That was the 2 meters. And there's my equal sign, and I'm going to have a 1/2. The mass is still 1.5. And the final velocity, this is a guy that is an unknown. Okay, so final velocity squared. Mass is 1.5. G is 9.8. And it's just going to fit my final height. My final height. Well, it's hitting the floor. I have no height. in the end. Okay. So now I'm sure you recognize a few things, but essentially this goes to 0. This value, if you work that math, you get 29.4 joules, units on here, units. This is, well, 1/2 times 1.5 is 0.75. And this is just final velocity squared. Still, this is 0 because that's 0. So there we go. And it's not a big deal to work this out. I'm going to end up dividing both sides by 0.75. And then these will cancel. Then I have to take the square root of both sides. Right. And I'm going to have a final velocity equal to 6.26 meters per second. Meters per second, that is velocity. Make sure units match with what you're talking about. So, box the final answer. There we go. Okay, so I found how fast this thing is going to be going right when it hits the floor. Awesome blossom. There's another way of doing this also. I'm sure when I got to this step and then this step right in here, you guys probably saw a couple shortcuts we could have done, right? So let's look at that down here. When I have this, first of all, you can say to yourself, well, the initial kinetic energy is 0 because I'm dropping it. There's no velocity. You kind of see this before you write it down. And so you know that this whole thing is going to go away. And then right before it hits the floor, or right, I should say when it hits the floor, it has no height. You see that ahead of time before even writing it down. So this guy goes away. Now this is specific just to this particular problem, but you're allowed to think this way, absolutely. So you have these two guys. That's all gone. That's all gone. All gone. All gone. You have these two guys, and where you work that out. And but what I'd like to show you though is not plugging numbers in before you've isolated the unknown. Well, here's what you got to do. You basically are starting with, I'm going to look at that. mg h initial equals 1/2 m v final squared. Okay, well, right away again I see I can cancel the mass. It's not a problem. I have to divide both sides by 1/2, which is the same as multiplying by 2, and that'll go away. Then I have to take the square root of both sides, right? So this is now g times initial height. I'm going to multiply that by 2 gh initial. And then I have to take the square root of both sides, so square root of that guy. And that is the thing I use. And I just plug a couple numbers in there, and I will actually get the same answer. It does lead to that. Yay! So, you can work it out this way and write it all out, and then show zeros. Or you can start to think ahead and say, you know what, I see those zeros ahead of time. There's no kinetic because we're dropping it. There's no final potential because it's at the bottom. It can't fall any further. And you can maybe save yourself a tiny bit of work. All right, now I want to look at one more example here of how you could use conservation of energy. Page 4, example number 2. Here we go. So we're going to have a 0.5 kilogram ball is thrown upward with an initial speed of 2 meters per second. And its location when we throw it (1 meter off the ground. It starts at 1 meter above the ground. So I'm given the situation here. I've got the description. I'm going to have to sketch this out real quick. But also, really, I'd like to know how fast will it be going when it hits the ground. So what is its speed when it strikes the ground? There's the question. Okay, well, let's check this out. We have the ground, and we have a ball. It's going to start at 1 meter above the ground. And so I can just kind of see. There is 1 meter. And it's going to start with an initial upward velocity. And essentially, it's going to do one of these things. It's going to go up, 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 up. And then stop and turn around, come back down. Gravity's pulling down. It's going to fall. Boom. Okay. So just like before, right? Just like before. At this location, here, and at this location here, I can identify a couple things. There's an initial mechanical energy there, and there's a final mechanical energy here. And this initial energy is a kinetic plus a potential, and those are initial values. This final is a kinetic plus a potential, and those are final values, right? Okie dokie. Now, since we're going to ignore things like drag, energy is conserved. There's energy in each of those accounts. We have that sort of labeled. In the beginning, we have both of these. You can see that there is kinetic. It's thrown upward with that initial velocity of 2 meters per second. That is a decimal point right there. But also, it's starting with at a location that gives it some potential energy. So it has this guy and it has this guy. Right when it hits the ground, there's only kinetic energy because at ground level, there is no potential. So I have this guy, but I do not have any of that. None of that. So here's the cool thing. I already have identified something I can leave out. And now, here we go. We're going to apply conservation of energy. There it is. In my initial, I have to use both of those. Initial kinetic plus, sorry. The pen is faster than the brain today. Initial potential, right? And over here for the final condition, for the final sort of status, there is kinetic and there is no potential. So, kinetic final. And what I've left off, I'll write it in a different color here. Let me use the blue. It should stand out enough. There. But that business, that guy right there, is 0. We've already figured out there is no potential energy at that location. It can't go any lower. So I simply need to work this out. I can break this down a little bit more. I can say, well, the kinetic is a 1/2 m v initial squared. This initial potential is an m g h initial. And I'm writing carefully. I'm keeping things sort of organized, easy to follow. This kinetic is a 1/2 m final velocity squared. And nothing to write here, because that guy was 0. That guy goes away, right? Okay. What do I recognize? I recognize that mass cancels, cancels, cancels. It's in every term, and it can go away. Oh, excuse me. So look at this. Where's my unknown? My unknown is the final velocity. It's this guy. I want to rearrange that equation and solve for final velocity first. I'm going to have to multiply both sides by 2. So this whole thing, multiply by 2 over here, and that's going to be 1/2 m initial squared plus, oops, the m canceled out, didn't it? Sorry. Cancel, cancel. So get rid of that guy. So I'm multiplying both sides by 2. And this is just now final velocity squared. Then I have to take the square root. But I should recognize something here. This is sort of going to simplify a bit. 2 times 1/2 is 1. So I have my initial squared. And then 2 times GHI is 2 GHI. And then I have to take the square root of both sides. Get that radical over everything on that right side. Left side, that's your left. And that's your final velocity. Okie dokie. Now I am simply left with plugging in some numbers. I know my initial velocity is right there. I know G is 9.8 for these problems. We're making the safe assumption that we're on our surface. H initial, the initial height, is that 1 meter right there. So 2 meters per second squared plus 2 times 9.8 meters per second squared. The seconds are squared. This was meters per second and the whole thing squared. This is meters divided by seconds squared. That's an acceleration, right? Times initial height was the 1 meter. I have to extend that radical, make sure I get it over everything, and it's now time for the calculator. And when I do this, the math is very straightforward. Multiply all these 3 together, then add 2 squared, which is 4. Then the very last step is take the square root of the whole thing. And when you do this, you get 4.86 meters per second as your final velocity in this situation, right? For this particular problem. Awesome. So keep a couple things in mind as you go about trying to learn these ideas. If you are asked to simply find the kinetic energy of something, you use the equation 1/2 mv squared. You have to know its mass, you have to know its velocity. If you are simply asked to find an object's potential energy, you use the equation mgh. You have to know its mass, you have to know how high it is above some reference line, and you have to know the acceleration due to gravity, and here on Earth it's 9.8. But those are just, sort of instant values. What is the kinetic energy at this moment? What is the potential energy at this moment? What if you're asked about changes? What is this new velocity? So are you looking for a new velocity? Are you looking for a new height? Then for questions of that nature, then you have to go to your conservation equation and use that guy. Very powerful stuff. Great ideas here. Okay, that is all for now. Thank you for watching. I'll catch you next time.